We are now going to look at an important discovery made by Maxwell Clarke, based on which he was able to justify the existence of an electromagnetic wave. In this video, our focus will be to state what displacement current is, to describe how Maxwell deduced the existence of displacement current, derive an expression for the displacement current, and finally state Maxwell's equations. Let's review Ampere's law, and that will help us today's lesson. We've learned in previous video that the closed magnetic line integral is always equal to the enclosed current multiplied by the permeability of free space. So we saw this diagram in which current is flowing through this wire and magnetic field is set up around the wire. We can divide the path of the magnetic field into infinitesimal elements or length, and then calculate the magnetic line product, the dot product of the magnetic field and the line at the point under consideration. We do so for all the small segments of the line and then add them all together, and that should be equal to the current enclosed multiplied by the permeability. That's what we said Ampere's law stated. Maxwell discovered something that made us understand that Ampere's law was not complete. So what he discovered modified Ampere's law, and that's what we are going to talk about. What he discovered we call the displacement current. Consider a capacitor that is connected to a battery. At the moment that the battery is connected and the switch is closed, this part of the battery, which is the positive terminal, begins drawing electrons from the one side of the plate. So electrons will be drawn from here because this side is positive. So electrons will rush from here to the positive terminal. And this side being negative will also pump electrons to this side. So there will be excess electrons on this side of the plate, and this side of the plate will also be deficient of electrons, leaving positive charges. As the current flows, what happens here? No charges will cross this boundary. So we don't expect current to flow through here. And Maxwell discovered something that behaved like the current flowing through this wire. From Ampere's law, if current is flowing through this wire, then magnetic field will be set up. The same thing happened when the electric field is building up here, even though charges are not crossing within this one. Here we are, the capacitor plate. At the moment, the capacitor is not charging and there is no magnetic field set up. When we move to this side, we realize that the capacitor is now charging. Electrons are moving away, and therefore current is in this direction as shown. So if current is in this direction, then there is magnetic field built up according to Ampere's law. Similarly, electrons are moving from the negative terminal of the battery to this side. So current is in the opposite direction. Again, there is magnetic field built up around these wires because there are actual particles, electrons, that are flowing through the wire. But when we come to the center part, Maxwell discovered that magnetic field is also built around the gap, and he wondered what was happening. there are no real charges flowing, but the magnetic field that is being built by the actual flow of current is now being set up again here, which means that there is an imaginary current flowing between the capacitor plates. Indeed, there is no actual current flowing, but what we are calling the imaginary current is actually the built-up of the electric field. As more electrons leave this plate and more electrons join this plate, the electric field in the gap grows. So as it is growing, it sets up magnetic field around the gap. So the build-up of electric field is what we call the displacement current. Now when we come to this side, during charging, the right-hand rule works for both the real and frictional current. Frictional current is what we call the imaginary current. If we use the right-hand rule here, we'll be able to determine the direction of the magnetic field. Similarly, we'll be able to tell the direction of the magnetic field. We can apply the same right-hand rule and determine the direction of the magnetic field. The direction of the magnetic field will be in the same direction as this one. But if we didn't know the direction of the current here, but we knew the direction of the electric field, which is positive here and the negative here, see the direction, then we can point our thumb in the direction of the electric field and determine the direction of the magnetic field. It will be clockwise if we were looking in the direction of the current. So when the capacitor is fully charged and the electric field is no longer burdened up, thus the electric field is now stable, it has a finite value, the magnetic field stops. All that it means is that changing electric field or electric flux has the same effect as current in a conductor. And the same changing electric field is equivalent to an imaginary current that we are calling the displacement current. So, in short, we are saying that there is an unseen current that is flowing between the gap of the capacitor, and it is due to the increasing or decreasing of the electric field. So changing electric field now creates magnetic field. That's the important thing that we need to keep in mind, and we are going to live on this one. Now let's do some mathematics with the displacement current here. From our lesson on capacitors, we realized that the charge on one plate of a capacitor can be evaluated by multiplying the capacitance and the voltage that is establishing that separation of charges. Then we also learned that the capacitance of a capacitor can also be calculated or evaluated from the design. If we know the area that is overlapping and know the distance that is separating the two plates, then we can multiply the ratio of the area and the gap size with the permittivity of free space, and then obtain the capacitance of the capacitor. Similarly, the capacitor will form a uniform electric field, so this equation also applies. Now we can substitute equation 2 and 3 into 1 and we will arrive at this. Realize that this product here, the area multiplied by the electric field, gives us the electric flux. Now we can differentiate through the whole thing with time. dq dt, that gives us the current. Then dE dt, if we differentiate everything here, this one is constant, this one, the area too is constant, so it is the electric field that is changing. So we differentiate the electric field with respect to time here. So this one gives us the current, and this one is constant here. We differentiate the electric field with respect to time. This one is here. Now we could also do the same thing to this one. We leave this one as constant and differentiate the electric flux with respect to time. So the current here is what we are calling the displacement current, and it is equivalent to what is here. Let's summarize the whole thing. From our introductory video, we said that a changing electric field could now produce a magnetic field. That's what we are seeing here. So if there is a displacement current that can produce an a magnetic field, then we need to modify Ampere's law to accommodate what Maxwell has discovered. So we are modifying Ampere's law. This is Ampere's law, and it's going out. We are now going to include a displacement current, and this displacement current must also be within the magnetic field line. So this displacement current can now be expressed as a changing electric flux, and the whole thing becomes Ampere Maxwell law. In simple terms, we are saying that there is real current flowing through wires, and there is imaginary current flowing between the capacitor plates. That makes up, whichever way we go, will create a magnetic field. A current flowing through a wire will create a magnetic field, and a change in electric field will also produce a magnetic field. Let me state it again. All that this means is that current flowing through a wire will create a magnetic field, as well as a changing electric field will also create a magnetic field. That's all that is contained in Ampere-Maxwell law or equation. Now, this was the last bit that was needed to bring together all the four equations that we call the Maxwell equations. Let's recap them to end our lesson. Now, the first equation that we started with was Gauss' law for electric field, and we said the electric flux over a closed surface will be equal to the total charges enclosed divided by the permittivity of free space. The second law is Gauss' law, but this time with reference to the magnetic field. It said the closed magnetic flux integral will always be equal to 0. Then we came to Faraday's law. We went through the motional EMF, and we saw that the electric field, if we find the closed line integral of the electric field, it should be equal to the changing magnetic field. That is, the EMF induced can be expressed as this and can also be expressed as this. So we equated them. That is the consequence of Faraday's law. Then finally, we have the Ampere-Maxwell law, which tells us that changing electric field can produce magnetic field. Okay, so try to review these. They may be very confusing. Sit down and then try to analyze the whole thing, and I hope you'll be able to get the key points in them for your successful exams that will be coming. Thank you very much.